Now we consider our first example to apply our new theorem. So we consider a binary symmetric source which puts out 0 and 1 with probability 1/2. The Hamming distortion and desired average distortion should be d smaller or equal than 1/2. To assume this, we need that the probability that x is not equal x hat is lesser equal d. Now let's look at the mutual information between x and x hat. That's equal the entropy of x minus the entropy of x conditionally on x hat. This we can write as 1 minus the entropy of x plus x hat conditional on x hat, where the plus is modulo 2. Because if we know x hat, then x plus x hat is known if we know x. Therefore, these two entropies are the same. Now we can estimate this by 1 minus h of x plus x hat, because if we remove the condition, we make the entropy bigger and therefore the expression smaller. Now look at the expression x plus x hat. If x and x hat are the same, then it's 0, and if they are different, then it's 1. But we know that the probability that x and x hat are different is smaller or equal d. So we can estimate this by 1 minus the binary entropy of d. And we get that the mutual information between x and x hat is greater or equal 1 minus the binary entropy of d. Can we assume this? So that's, of course, that's a bound. So the question is, can we assume this bound also? And if you recognize your lecture of information theory, then you know, if you look at the binary symmetric channel, where you have the crossover probability 1 minus d, then you get exactly this capacity, 1 minus h2 of d. Now our source produced with probability 1/2, 0, and 1. Now we can choose our channel from x to x hat just as a binary symmetric channel with this crossover probability d. Then, of course, if you look at the capacity, then we get 1 minus h, the binary entropy of d, and we exactly assume our value.